let's take a look at how we can name ionic compounds. Again, remember, an ionic compound will typically be composed of a metal and nonmetal, or of a metal or nonmetal in combination with one of the polyatomic ions on the list of the table that you have to memorize. So when you're naming ionic compounds, you have to remember that you don't put mono, di, tri, tetra to indicate the subscript that's there. Those are the rules for molecular compounds, not for ionic compounds. And you also have to remember that the metal ion will need a Roman numeral if it's one of the ions that can have more than one charge. So which metals never need Roman numerals? That would be group 1 would never need a Roman numeral, group 2, and those 3 transition metals or post-transition metal that I had said that you need to memorize, and that is aluminum is 3+ always, so it doesn't need a Roman numeral. Zinc is 2+ always, so it never needs a Roman numeral, and silver is 1+ always, so it never needs a Roman numeral. And that's easy to memorize because it's on that staircase, that 3-2-1 staircase, which on the periodic table looks something like this. Al's 3+, zinc would be 2+, silver would be 1+. So let's start examining some of these ions and just kind of doing a step-by-step as we go. Let's just take this first one that's here, Na2SO4. So I can tell it's an ionic compound. I have a metal with a polyatomic ion, and I see right away that the metal is a group 1 metal. It's sodium, and sodium always has a +1 charge. So I don't need to go through work of finding what the charge is. I know the charge, it's +1. So I'm just going to go ahead and I'm going to start naming this right away. This is sodium, because Na is sodium. And what's sulfate? Oh, there we go. And SO4 is sulfate. And I know that because that's on the polyatomic ion table. If I go to the formula, why is that 2 there? That 2 came from the charge of SO4. Because Na is +1, I need 2 +1 charges to cancel out the 2- charge of the sulfate, and hence that's my empirical formula. I don't need to put in any work to figure out the charges, to figure out a Roman numeral, because this sodium only has 1 charge +1. So I just name the positive ion, sodium, and I name the negative ion, sulfate. If this were Na2S, let's say, instead of sulfate, how would I name this? This would then be sodium sulfide, because anytime I have a nonmetal from the periodic table that has gained electrons and now has a negative charge, we name the ion ending in IDE, sulfide. So if it's a polyatomic ion, I keep the ending. If it is a monatomic ion, then it's going to end up ending in "ide." So let's look at another one. Let's look at the next one. AgNO3. Okay, I see Ag. Silver is one of those ions that I have to know the charge of. It always has a +1 charge. So I can just go ahead and name this without a Roman numeral. This is just silver. And NO3 is from my polyatomic ion table. That is nitrate. So this is silver nitrate. No Roman numeral needed. Very easy to name when I don't need a Roman numeral. Let's look at the next one. PbPO4. Actually, I don't like that one because that one doesn't really make sense in life. So I'm going to pick a different one. I'm going to do MnO2. If I look at Mn on the periodic table, it is a transition metal. It is not one that I know the charge of. It has more than 1 charge. So when I name it, I need to indicate the Roman numeral in the name so that the other person or whoever, if this is in the lab, who's ever using this chemical knows which formula it is, which chemical it is, because manganese 3, manganese 4, manganese 7, all have different formulas when combined with oxygen, and those all have different properties as well. So what I like to do, you can do this on inspection or you can do it with a formula, and I'll show you kind of both ways. If I'm doing this on inspection, you always look at the charge that the metal, or look at the other ion that the metal's combined with. Oxygen, okay? I know the charge of oxygen is always -2. Okay, so if I'm doing this on inspection, I take into consideration the subscript and the charge of the other ion. Okay, oxygen, there's 2 of them, and they each have a -2 charge. So in total, there's a -4 charge. What does the charge of manganese have to be to cancel out that negative charge? And the answer to that is it has to be +4. So this is manganese 4 oxide. If you want a more concrete mathematical way of doing it, what I would do is I would put an X above the manganese, and I would make a formula. What I do is I take the top number, the charge, and I multiply by the subscript. And I do that for each ion, adding it together till I get to the end, and I set it equal to 0 because this is a neutral compound and positive and negative should cancel each other out. So again, what I'm going to do the charge of manganese is X times the subscript is 1 for manganese, okay, plus. Okay, I've got 2 oxygens, which each have a -2 charge, and I set it equal to 0. That's X minus 4 equals 0, so X is +4. Okay, so that means the charge of manganese is 4 plus, as we said upon inspection, and this is manganese 4 oxide. Let's try another. Let's try this one. PbCO3 2. Okay, again, let's inspect this. I see that I have Pb, a metal, which is a transition metal that has, or even a post-transition metal, but that has more than one charge. I'm not sure what it is, so I'm going to give it an X. I'm going to figure out what the charge is because I need to put that charge as a Roman numeral. I can't name it until I know the charge of it. And CO3 is a polyatomic ion. It's from our ion table. It has a -2 charge. Okay, so I can do this on inspection. CO3 has a -2 charge, and there's 2 of them. 2 times -2 is -4. So what does lead have to be to cancel out a -4 charge? Oh, okay, it has to be a +4 charge. And I can do this mathematically as well. I'm doing charge times subscript for the first. Pb has a subscript of 1, 1 times X, plus subscript of 2 times -2 equals 0. Notice I did not touch the subscript of 3. That is not the subscript that tells me how many ions I have. That's the subscript that's part of the ion. So if I'm looking at a polyatomic ion, I only multiply by a subscript outside of parentheses if there is one. And to help me from using a subscript that I don't want to use is, for me, whenever I'm doing this, I will add parentheses to any polyatomic ion that doesn't have them already. And I'll show you what I mean next. Okay, so again, this is X minus 4 equals 0, X equals +4. So this here is lead, because Pb is lead, something to know, 4 carbonate. You can always go and double check your work. Lead 4 is Pb4 plus, carbonate is CO3 2 minus. When I flip them, I get Pb2, CO3 4. That simplifies out to what I originally had. Let's look at this if it were a little bit different. Let's say instead, to start with, I had PbCO3 only like that. Okay, again, I have Pb. It has more than one charge. I got to figure out the charge before I name it because the charge will be the Roman numeral. Okay, so Pb's X. CO3 is a polyatomic ion, and notice that there are no parentheses around it. For now, I am just going to add parentheses. And why am I doing that? Because I do not want to use that 3. I don't want to accidentally multiply by that. That is part of the formula that has the charge. It is not a subscript that indicates how many ions I have. Okay, I have 1 CO3 right now. So if I want to put a 1 outside of parentheses to remind myself there's only one of those CO3s there, I'm really multiplying any charge that it put there, minus 2, by 1. So if I'm looking at this on inspection, I say, okay, CO3 has a minus 2 charge, Pb's got to have a plus 2 charge to cancel this out. If I'm doing this mathematically, charge times subscript, x times 1 is x, minus 2 times 1 is minus 2, set it equal to 0. I get x is equal to positive 2. So this one is lead 2 carbonate. Let's look at these two others. Let's say I have CuO and Cu2O. Again, Cu is a metal that has more than one charge. It's a transition metal. I'm not sure what it is in either case. And in both cases, I know that O is a minus 2 charge. So in the first one, there is one oxygen. It has a minus 2 charge. Cu has to be plus 2 to cancel it out. So that top one is copper 2 oxide. If I wanted to do it mathematically, charge times subscript for the first, x times 1 is x. For the second, minus 2 times 1 is minus 2, set it equal to 0, x is equal to positive 2, so that confirms that it's copper 2 oxide. For the bottom one, on inspection, O is 2 minus. There are 2 copper ions that would have to cancel out that minus 2 charge. So each copper would have to have a plus 1 charge. So that would be copper 1 oxide. To show that mathematically, charge times subscript for the first, 2 times x is 2x. Minus 2 times 1 is just minus 2, set it equal to 0. 2x equals 2. X equals positive 1. That confirms that that is copper 1 oxide. Again, if this were a polyatomic ion attached to it, let's say this were CuSO4, I can do this on inspection. Cu is an X, SO4 is a minus 2. There is only one of them. So to cancel out the negative 2 charge, copper has to be plus 2. Remember not to multiply by a subscript unless it is outside of parentheses for a polyatomic ion. I am talking about there only.